Morning, good afternoon, everyone. Today we will be talking about linear combinations and spanning sets. Let's start with linear combination. Let's take a look together at a definition of a linear combination. What is a linear combination? A vector A is called a linear combination of vectors B and C if there are two scalars K and L, so that vector A can be written as A equals KB plus LC. What is the first thing that we notice about this definition? First of all, my communication is horrible. I talk about vector A, but my notation is far from what it should be. I talk about vector B, I talk about vector C, so let's make sure the notation is correct. Vector A again, vector B, and vector C. Good. Now, how about K and L? Should I put vectors on top of K and L? The answer is of course no, because K and L are scalars. That's a keyword. They are real numbers, so definitely I do not need to put the vector notation on top of them. Good. So we have an idea about the definition of this of linear combination. Now I have a feeling that this definition doesn't really answer your question, what is a linear combination? As usual, to understand that, what I want to do, I want to understand this definition in a context. Let's understand it in a context. Have we seen something like that before? Well, as you can see here, I have a vector. Let's call this my vector A. What is the notation I need to use for this vector? It is a vector 3 and 2. So vector A. How can I write this vector as a linear combination of some other two vectors? That's the idea. Write it using two other vectors. Well, the first one that should come to your mind are our old friends, vector I, unit vector I, and J, right? Now, I need to multiply by my I by 3 and my J by obviously 2. Good. So did I write my vector A as a linear combination as I have it here in the definition? Sure, I have it. My two vectors B and C are nothing else but I and J, very special vectors but still vectors, and my two scalars K and L are right here. So it seems like we've been doing this before. It's not the first time we do that. Now, the next question is, can I write vector A as a combination of two other vectors that are not unit vectors? I don't know. Let's try to do that. As you can see here, the black vector here is again the vector 3, 2. Is the same vector A, 3 and 2. Now, I want to write this vector A as a linear combination of the blue vector. Let's call the blue vector B. How do I write vector B? Well, the x-coordinate is 2, the y-coordinate is -4, so there you go, B is 2 and -4, that's my blue vector, and then my red vector is vector C, and the coordinates of vector C are 1 and 2. So, two random vectors. Can I write the black vector as a linear combination of blue and red? I did a little bit of calculations for you, and look what I noticed. I noticed that I can write 3, 2, if you take a look right here, we notice that I can write 3, 2, which is nothing else but my black vector as linear combination of 2 and negative 4. This is nothing else but my blue vector, and 1 and 2 is nothing else but my red vector. So I notice that I can write 3, 2, the vector A, as nothing else. So this is vector A. I can write it as 1 over 2 times blue, which is B, plus 2 times red, which is C. So what are my scalars in this case? My scalars are 1 over 2 and K and L 2. Good. Now let's make sure that my algebra is correct. You know, I have a hard time with my algebra. So I have to check that 3 equals 1 over 2 times 2, that's 1, plus 2 times 1, that's 2, 2 plus 1 is 3. My x coordinate is okay. My y is 2 needs to equal to 1 over 2 times negative 4. So that's negative 2. 2 times 2, that's 4. 4 minus 1 is, oops, am I wrong here? No, it's minus 2 plus 4, that's 2. So yes, both x and y are correct. Beautiful. Algebraically, life is good. Now let's see if life is good when I try to interpret this graphically. How am I going to interpret 1/2, this part, 1/2 of this part over here, 1/2 of the blue vector? Well, that means the direction stays the same, just that the magnitude is half of what it used to be. So there you go, approximately half must be this. Maybe a little bit shorter, but anyway, we have an idea. But that's a vector 1 over 2 times b. What is the meaning of the second part here? Second part over here. There you go. 2 times 1 over 2 times vector c. That means take vector c and double it, right? Double its magnitude, maintain the same direction. So I take this, I double it. God, where is that? It's somewhere over here. Good. Guess what happens when I add my new vector, my new blue vector, and my new red vector? I'm gonna get nothing else but vector A. There you go. I do my parallelogram. If you want to do your triangle, nothing stops you. Move one of them, and you know how to do the triangle. Good. So what did I accomplish here? I wrote the vectors 3, 2 as a linear combination of 2 other vectors, the red and the blue. Good. Now your task is, I wanted to use the same vectors B and C, and I want you to write these 3 vectors that I have here, 7 and negative 2, negative 5, negative 2, negative 1 million and 00001 or whatever I have there. I want you to write all these 3 vectors as linear combination of the 2 vectors that we used before. So I want you to write them as KB plus OC. Do you think you are able to do that? Yeah, the algebra will get messy, but you won't be able to write. If you do a little bit, if you try hard, I'm sure you can figure out your scalars there. Oh God, I have this again. Your scalars here, K and L, so that each of these 3 vectors here can be written as a linear combination. Can you think of any vector? Can you think of a vector that cannot be written in terms